Welcome to section 9.19. This is the 93rd session of the CISSP exam prep series. In this session, we'll cover the core mechanisms that keep a system trustworthy from the inside. Why should you never simply trust software? How does an operating system keep processes from stepping on each other? What does hardware add that software cannot? Where does a system's chain of trust actually begin? And how does a security policy shape a system from the very start? Why does this matter beyond the exam? Because these mechanisms are the quiet foundation under everything else you build. Picture a payment platform that runs dozens of third-party plugins side by side. If one buggy or malicious plugin can reach into another's memory, the whole platform is compromised. The controls in this session are what stop that from happening. As an architect, you design them in, or you inherit the consequences. So why should you never simply trust software? Because any code written outside the operating system is, by default, unproven. This is not about assuming every program is evil. It is a protective stance. Since third-party software comes from someone other than the operating system maker, it might misbehave, so the system treats it as potentially harmful and isolates it. That is the principle of zero trust, applied right down at the machine level. And the time to build these protections is early, during design, not bolted on at the end. Think of a bank that assumes no visitor is pre-cleared and routes everyone through the same controls. When security is added only after the building is finished, it almost always fails. How does an operating system keep processes from stepping on each other? Through process isolation. The operating system gives each process its own separate memory space and then strictly enforces those boundaries, so one process cannot read or write another's data. This does two things at once. It blocks unauthorized access, and it protects the integrity of every process. Without it, one poorly written program could scribble into another's memory and crash the whole system, or a malicious one could reach in and attack its neighbors. Many systems deliver this by giving each process a virtual machine view, where it behaves as if it owns the entire computer. Think of soundproof studios along a hallway. Each performer works freely, unaware of and unable to disturb the others. What does hardware add that software cannot? Hardware segmentation serves the same goal as process isolation, keeping one process away from another's information, but it enforces the separation with physical hardware controls rather than software rules. That makes the boundary far harder to defeat, but it also makes it expensive and complex. So you tend to see it only where the stakes are extreme, such as national security systems, where the sensitivity of the data justifies the cost. Think of the difference between a locked office door and a separate reinforced vault building. Both keep people out, but one is a far stronger, far pricier barrier. Where does a system's chain of trust actually begin? At the root of trust. This is the anchor point from which every other security assurance flows, the foundation for verifying the integrity, authenticity, and confidentiality of what the system does. At its heart sits a trust anchor, a component that is inherently trusted and deliberately made tamper-resistant, because the trustworthiness of the whole system is derived from it. The strongest form is a hardware root of trust, built into dedicated chips, such as a trusted platform module or a hardware security module, which isolate cryptographic keys and operations from the general computing environment. Think of the master key kept in a sealed, tamper-evident case. Everything else in the building trusts a lock, precisely because that one key is protected. How does a security policy shape a system from the very start? A system security policy guides the design, development, testing, and maintenance of one specific system tightly targeted to that single effort. For developers, it takes the form of a document defining the rules and procedures for how the system manages, protects, and distributes sensitive information. A policy that specifically prevents information from flowing down from higher security levels to lower ones is called a multi-level security policy. The crucial point is timing. Security must be considered across the entire life of the project, applied to hardware, firmware, software, and how people use the system. Think of a blueprint that bakes in fire exits and load-bearing walls from the first sketch. Try to add them after construction, and the result is fragile. So let's bring it together. You start from the premise that software is untrusted, which is zero trust at the machine level, and you design protection in early. Process isolation gives each process its own guarded memory, while hardware segmentation enforces separation physically for the highest stakes systems. The root of trust anchors every assurance, strongest when built into dedicated hardware. And a system security policy shapes one specific system across its whole life, sometimes controlling flow between security levels. Master these, and you are building trustworthy systems from the foundation up. The MCQs covering all the topics and concepts from this session are available on rucloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session.